Welcome stats students. We're in section 9.1 and this section we talk about an introduction to statistical tests. And this is kind of one of the really big ideas in statistics. It's what we call a hypothesis test. And from the hypothesis test, we'll be creating something called p-values. And these are kind of some of the main things you see. If you see statistics kind of being used out in the wild, these are the types of things that you see people doing. So it's really important that we understand what this test means, we understand how it's used, and then so that we can interpret and understand when people use these words. This section I will break into two videos. Video number one will kind of introduce the statistics, introduce the idea of statistics, and we'll do a problem or two. And then video number two, we'll just do some more problems from the notes. One of the things you have to do is do a bunch of problems in order to make sense of all this. Okay, so let's begin. The big idea of a statistical test is this picture I've drawn over and over again. It's the difference between a sample and a population. So what we do is from a sample we find something like, say, the average x bar, and then we have a population average, which we call mu. Last time when we talked about confidence intervals, what we did is we used x bar. We said, hey, we know what the average is. Can we guess what mu is? That is, can we figure out a confidence interval or range of values in which the mean should likely occur? And this is a super important calculation, and actually to a lot of statisticians, that's probably the most important calculation. So in some ways that confidence interval activities maybe is even more critical than what we're going to do today. But what we're going to do today is super important because this is the way the statistics has traditionally been done, and it's what you'll see when you read papers, and it's what people expect when you write papers. So today what we're going to do is we're going to start with an assumption. We're going to start by assume that mu is some given number. What number is it? Well, that depends upon your problem. So usually mu is whatever kind of default is, whatever the default is for your population. If you're giving an exam, mu is the average of the exam that over millions and millions of students. If mu is the height, then mu is the, if you're studying height, then mu is the actual height of, say, college students throughout the United States. And then what we want to ask is we want to ask the question about our sample. We want to say, is our sample unusual? So that's kind of the main question that we're asking whenever we do statistical tests. So what we're trying to do is we're not trying to estimate the average, we're trying to take a known average and ask, is our sample somehow different or unique compared to the whole average? Now you might see why this would be important, because if you're doing some sort of research study, you're examining something, what we're usually trying to analyze in those research studies is we have some sort of group that we've studied, we've given them an experiment, we've done something, we go, and I think this group is different from everyone else in the population. And so a statistical test is meant to detect differences between your sample and the entire population. So how do we do this? Let me just do a little bit of overview talk for a while, and then we'll move into actually talking about some more specific problems. So the overview just goes like this. We make an assumption, and our assumption is always going to come in the form of what we call a null and alternative hypothesis. So our null hypothesis is going to be H naught, and we'll write mu is equal to some number. Now, please don't write a number or hashtag sign when we get into the problem. This number is kind of whatever our default is. And so this number, it would be the average if there is nothing interesting about our sample. So we always start with an assumption. The assumption is the assumption is that our average is what occurs if there's nothing interesting in our sample. And then what we do is we compare that to our alternative hypothesis, which we'll call H1. And our alternative hypothesis will be written in one of three ways. Either we'll do mu is greater than that number, or we'll write mu is less than that number, or we'll write mu is not equal to that number. So we'll write one of these three results. So I'm just going to put them all right here, knowing that you only write one at a time. And how do we choose which one? Well, it depends on your study. So if you're trying to prove that that LCU students are taller than most college students, then your H1 would be bigger than whatever your number is, than whatever the default height is. If you're trying to prove LCU students are shorter, then your alternative hypothesis would use a less than. And if you're just trying to prove that LCU students are different in some way, then we would use a not equal to. So this is how we're going to set up our hypotheses. So the first thing we do is we make a hypothesis. Now then, based on that hypothesis, we find the probability of our sample. So we have our hypothesis, then we have a study. So we know the average height of college students throughout America. And then we take our sample of our students at LCU, and we want to ask, are LCU students smaller, taller, or a different size than the entire population? So what we do is we try to find the probability that our sample could have happened just by chance. And this means that what we'll do is we'll use some sort of normal distribution. We'll put our sample will create a number here. We'll have to talk about how to come up with this number, because it's not just the number from our sample, but our sample will create a number right here. And what we'll do is we will find this probability. And so P is the probability that shows up over here. So again, I'm just giving you an overview. We'll go into detail on all these pictures. But this is the big idea of a hypothesis test. You make an assumption. The assumption is that nothing interesting is happening. You then find the probability, and that is the probability that your sample could have occurred if nothing interesting happened. And then finally, we draw conclusions. And it turns out there are only two possible conclusions that you can ever have for a problem. Either your P is very small, and if P is very small, then that means your assumption is probably wrong. So say, for example, we made the assumption that our students were whatever the height of a college student is. I don't know, say 5'8" or something. So we said LCU students are 5'8", and then our sample, our LCU students were so much taller than that the odds of us just picking out students with that height by coincidence would have been, say, less than 1 in a million. Then you can go one of two ways. Either you got lucky and you just picked the tallest students you could ever find at LCU, or LCU students are actually taller than the rest of the population. And so those are the two possibilities. Either you got lucky and you happened to randomly select tall people, or your sample or your population has taller people than the whole rest of the country. And if your P is very, very small, that means that the probability of you selecting these people by random was almost zero. So if it's very small, then what we'll assume is our assumption was wrong. Our assumption is false. So if P is very small, we assume our assumption is false. Now, if P is not very small, I'm going to say large, but maybe I'll just say not small. Then we'll assume our assumption is not false. I'm not going to say true. So this is an important distinction. I'm never going to prove that my assumption was a true assumption, because if our probability had even, say, a 50% chance of occurring, it doesn't mean our assumption's true. Our assumption could have been true, or it could have been false, and our sample just had the same numbers as they would have had if our assumption was true. Maybe that makes a little bit of sense, and that is that we can't prove our assumption true, we can only prove the assumption false. And this is an important idea as we go through this problem. So here's the overview of how we're going to do these things. An overview is we make an assumption, we then find the probability of our sample, and then we draw conclusions from our sample. So let's start with this big idea of making an assumption. And I'm going to pick an example from the news because we're all in this coronavirus thing together. So I thought I would start by kind of talking about a problem that I thought was actually really interesting. And that is that there is a company called Kintsa, and they're making smart thermometers. And Kintsa is a company that makes thermometers, and you take your temperature, and their thermometers are connected to the internet, and so they gather all of your data. And so people all over the country own these thermometers. They're taking their temperature, and then as they take their temperature, it gets recorded to Kintsa's database, and so they have a record of people's temperatures all over the country. Now, by the way, if you're like me, you're asking two questions. Question number one is, why would I want my temperature to be connected, my thermometer to be connected to the internet? I mean, in my opinion, not everything I own needs to be connected to the internet. I don't know if my water bottle needs to be connected to the internet. So, I mean, or my socks. I mean, so I don't think everything I own needs to be connected to the internet. And if you're also like me, you're saying, do I want this company to just own my temperature data and to keep it in a database? I don't know. So if you're uncomfortable with that, you're probably like me. But some of you may be saying, hey, this is great. If I recorded my temperature on the internet, then I could track it, and maybe this company could help me track my temperature, and then I would know more about my health. Okay, so there you go. It all depends on whether you trust the company or not. But regardless, this company has done a fascinating research study just the past few weeks, and that is they know how many fevers to expect to show up in Lubbock. And that is, they know how many people own their smart thermometers in Lubbock, and they know how many of them will take their temperature, and how many of them will take a temperature that has a fever recorded in it. And so if this were a normal year, they might expect, say, 9,000 fevers in Lubbock. Okay, by the way, this number is completely made up. I didn't know what a normal number is. This would represent about 3% of the Lubbock population. That seems about right. Maybe at any time, 3% of the people have a fever. Maybe that's a little high. I don't know. But Kintsa knows that at the end of March or at the beginning of April, you would always expect there to be about 9,000 fevers in Lubbock. Well, what they can do is they can use their data and find out how many fevers are actually in Lubbock. And so you see, now we're in this story where we assume that the population has 9,000 fevers, and now we ask, is our sample, or the people taking our study, do they have a different number of fevers than what we would assume? And what can we see? Well, we can see that if the coronavirus is hitting Lubbock really hard, we should expect there to be more fevers. And we would see that there are more fevers in Lubbock if the coronavirus is really hitting us hard. If we're kind of doing a good job of social distancing and fewer people are getting sick because of our social distancing, we might even have fewer fevers than 9,000. So you can see how this company could use this data from their sample and compare it to the expected average and be able to create a hypothesis test. So now we'll talk about how might we create hypotheses. So we might have a null hypothesis. And the null hypothesis would be what to expect if nothing interesting is happening. There's nothing going on. Nothing to see here. So that is, the null hypothesis is that it's just life is like normal, and there's nothing to see here. And the null hypothesis for this situation, if we have 9,000 fevers in Lubbock, the null hypothesis is that mu is equal to 9,000. So it's a normal year. There's not any exceptional viral outbreaks. 9,000 is what we'd expect. Okay, so we're going to write H naught mu equals 9,000. But what about in a strange year? This is the alternative hypothesis. Well, you can guess that if coronavirus is running wild, that we would have a lot more fevers due to coronavirus. So our alternative hypothesis is that we get more fever due to coronavirus. Here, I'll just put COVID. Okay, so what we can do is we can now test this hypothesis. If there's nothing going on in Lubbock, we would have 9,000 fevers. If there is something going on in Lubbock, then we would expect our number of fevers to actually be bigger than 9,000. And then what Kienza can do is they can now take their thermometers to find out how many fevers are in Lubbock, and then use their sample to compare to this 9,000 to see whether their alternative hypothesis, whether their null hypothesis is true or false. So the first part in doing any sort of research study is to say, what would be the answer if nothing interesting is happening? What would be the answer if something interesting is happening? Okay, so what I want you all to do is read those first three problems on exercise 9.1. So exercise 9.1 has three problems. I want you to read those. Pause your device right now. See if you can write out a null hypothesis, H0, and an alternative hypothesis, H1, that represents those problems. So pause right now and come right back. Okay, hopefully you did pause. If you didn't, well, you should be ashamed of yourself and go do some sort of activity that reinforces your shame. Okay, no, I'm just teasing. Don't worry about it. But okay, so let's look through each one of these. The first one, a teacher knows that students will average a 78 on a standardized exam. However, he believes that students at his school are exceptional and that their average on the exam will be better than the national average. For what's our null hypothesis? Our null hypothesis, which we always write with an H and a little 0, our null hypothesis is that the average is equal to 78. Because notice, if there's nothing happening in this problem, if these students are the same as every other students in the country, then we should have an average of 78. However, what the teacher is hoping to prove is that the students actually have an average greater than 78. So our alternative hypothesis is that our result is greater than 78. Okay, so there's that first one. The second one, a track star averages 53.54 seconds in the 400-meter dash. This is faster than I ever ran a 400-meter dash. I ran 400-meter dash in high school, but our school didn't take track seriously. We were a football school, and we mostly did like football exercises all week. And then on track day, we would show up completely unprepared and get demolished by all the other schools. And so there you go. But I ran 400. I never ran this fast. Okay, but what's our alternative hypothesis? We have our track athlete who runs this fast a 400-meter dash, but she is trying a new training regimen and hoping that she can make her training time even faster than that. So our alternative hypothesis, if the training regimen is the same, is normal, doesn't do anything to her time is going to remain at 53.54. So that's going to continue to be her average with this new training regimen. But what if her training regimen works? If her training regimen works, we know that the average would be smaller because faster in track means that your time goes down. So our time would be 53.54. And so what you see is we see the null hypothesis, nothing happens, versus the alternative hypothesis, the training regimen worked. It made something change. Okay. Finally, part C, a scientist notices that something's not quite right in his weekly pasta dinner. So he wants to test whether the average amount of sodium in the pasta is different from the recommended 3 milligrams per cup. This scientists do strange things, so maybe the scientist does that as well. Okay, so if nothing happens, if the pasta is following the recommended dose and doing exactly what you'd expect, then that means the average would be equal to 3 milligrams. But what if there's something different about the pasta? So the scientist is going, maybe something's wrong here. If something's wrong here, then what would that mean? It would mean that it's not equal to 3 milligrams. So notice that this scientist, I don't have to write the milligrams. In my handwriting, it's kind of sloppy. Notice that this scientist doesn't care whether they have too much salt or too little salt. They just want to detect, is the salt different from whatever we started with? Okay, So these are how we write null and alternative hypotheses. Get really good at this because every time we do a problem, you'll be asked to write null and alternative hypotheses. Write these down correctly and you get like a free 2 points. Now 2 points out of 10 is not great, but it's better than not having 2 points out of 10. And if you can't write these down, you're not going to be able to move forward on your problem. So get really good at writing these things down. Okay, the next thing we want to ask ourselves is what do we do once we have our null and alternative hypotheses? Well, once we have our null and alternative hypotheses, we want to ask a question, and the question is how likely is the result that we got? And so what we're going to do is we're going to create a test statistic. And all a test statistic really is a way of comparing our results. It's just a way of placing our results on a normal distribution. There, that's the word normal. That's the word distribution. I know it looks messy. So all test statistic is it's a way of taking what we got for our sample and putting it on a normal curve. Why is this good? This is good because then we can find some probabilities associated with that normal curve. So what we're going to do is our test statistic is going to look like this. It's going to say z is equal to x bar minus mu divided by sigma over the square root of n. And what you'll notice is that this looks just like that z-score that we've had before, except this is the average that we get from our sample. This is the mu that we got from our null hypothesis. And this is the standard deviation that comes from whenever we find a standard deviation of a sample. So this comes from the central limit theorem. So you'll remember if you did the central limit theorem, the average should stay the same, but the standard deviation becomes sigma divided by the square root of n. So let me take that formula and talk about it just a little bit more. Divided by sigma over square root of n. This number, whatever this number is, this is from your sample. And I say your, right, when you read the textbook will create their own sample or things like that. But if you're doing a project, if you're doing an experiment, if the person in the textbook is doing a project, is doing an experiment, this is the average from the sample. This is always the number from your null hypothesis H naught. So this is what the average would be if nothing interesting is going on. So if we're doing smart thermometers, then this 9,000 is going to be the number that goes right here. If we're doing the problems from earlier, 78 would go right here if you're the teacher. If you're the track athlete, 53.54 would go right here. If you're the scientist, 3 would be the number that goes right here. So this is always the number that comes from your null hypothesis. So this number you should always get right. There's no reason to put the wrong number in that spot. And finally, this sigma is the standard deviation from your population. And so this is standard deviation from the population. And this would have to be given to you in your problem. So notice sometimes you'll know what the standard deviation is. So for example, if you are this teacher and you're doing a standardized test, it might be that your standardized test has plenty of data that you know what the standard deviation should be. For example, if you're talking about SATs or ACTs, those tests are so widely used that the people who develop them, they know what the average score for the test is, and they know what the standard deviation is for all the students who take the test. So sometimes that standard deviation is known and it's given, and you can put it right here. If, however, you're this track runner, you probably don't know the standard deviation, and so we'll talk in just a second about what to do in that case. And finally, n is the size of your sample. Is the size of your sample. So if you're this teacher who's giving out tests, this is how many people are in your class. If you're the track athlete, maybe you try running the 400 10 times, and this is 10 would be the number of times that you timed yourself. If you're the scientist, maybe you've taken different samples of your pasta, and this is how many samples you've taken. So this is the size of your sample, how many items are in your sample. Okay, now let's come over and let's talk about the test statistic, because we actually made a big assumption in the test statistic. There are actually going to be two test statistics. One test statistic is what we use if sigma is given, and that's going to be z equals x bar minus mu divided by sigma over the square root of n. The other test statistic is going to be if sigma is unknown. Now, if you're playing along at home, you might be able to anticipate what's going to happen if sigma is unknown. Whenever we did confidence intervals, when we switched from when we knew sigma, we put it in one formula. When we didn't know sigma, what did we use instead? Oh, that's right. I heard you all the way at your home, even in the future, that what we put in the inside is S. So instead of using sigma, we use S. And we do the exact same problem, except now we're going to do T instead of Z. So we switch our Z to a T, and we switch our sigma to an S. What's the only difference now? The difference is this S is from your sample. So sigma would have to be given for the whole population. So for example, if you were the teacher given the test, you would have the standard deviation for the entire population, everyone who could possibly take the test. If you don't know that, if all you know is the average, then maybe you're going to use S, because S would be the standard deviation of your 20 students who took the test. And this is going to be a little less accurate than the sigma, so we're going to use a T distribution instead of a Z distribution. Okay, so this is the basic idea of a test statistic. Now, what I want to do is, what do we do with this T and this Z and this T distribution once we get to it? Well, what we do is we find the probability of this outcome or something more extreme. So let's look, for example, at this Z problem. And if we have a Z, then what we're going to have is we're going to have a normal distribution. We will have whatever our outcome is. So this is the Z that we calculated up here. And then what we'll do is we'll calculate this probability. This probability will be P. So what I want to do is just take just a second and look at those three problems that we did earlier. And those three problems we did earlier, we're going to think about them each just a little bit differently, depending upon how. I didn't mean to erase that. We're gonna think about them all just a little bit differently, depending upon how we wrote our hypotheses. And this is where we have what we call a one-tailed or a two-tailed problem. So let's come look at those three hypotheses again and compare them all. Okay. So I'm going to try to do this and see if I have enough space to see everything. All right, there we go. And I think we can kind of see everything now. So on this first one, notice what we're going to get is we're going to get a distribution that looks something like this. And we're going to calculate our Z value to be right here. And notice, because we're interested in greater than, we're going to calculate the greater than part of our normal distribution. So every time I do one of these problems, I'm going to draw myself a bell curve. I'm going to shade in the bell curve, and P is going to be the part that I shave. The greater than tells me I'm shading in the part greater than Z. And we call this, maybe not surprisingly, a right-tailed test. So it's right-tailed because we're shading in the right-hand side of our test. For our second problem, we're going to have this track athlete. The track athlete is going to calculate a number right here. I'm going to call it Z. And then, well, the track athlete wants their time to be less. So the track athlete's going to shade in this part of the problem. And so for the track athlete, P is going to be this left-hand side of the problem. And so this is, not surprisingly, going to be called left-tailed. A left-tailed study. Now finally, we have the scientist, and notice that the left-tailed comes from the fact that we're using a less than on the alternative hypothesis. So our null hypothesis tells us which number goes into our formula. Our alternative hypothesis is telling us how we're going to shade our picture once we set up our probability. Okay. Finally, what about the scientist? Well, the scientist is going to gather a number, but they're interested in not equal to. So it could be not equal to by being too big, or it could be not equal to by being too small. So the scientist is actually going to put two different sides here and is going to shade both sides and put them both together. So the scientist is going to have P is going to be both sides. And so this, again, not surprisingly, is called a two-tailed test. And so what you can see is that we have the three ways we could have written our hypothesis. We could have written it as greater than, less than, or not equal to. And that tells us whether we get a right-tailed, left-tailed, or two-tailed. The nice thing about a two-tailed test is that what we can do, if you have a two-tailed test, you can just take one tail and multiply it by 2, and then you get your two-tailed test. So, for example, if I were to calculate just this side, then I could calculate that side and multiply it by 2, and that would give me my two-tailed test. So multiplying by 2 is really easy. And you can see that from the picture. So I will always draw my pictures. Okay. And so what we're going to do is we will, what we'll do when we do a problem is we write our hypotheses, we then write our test statistic, we then draw our picture, and then we calculate the probabilities on the outside. So I think we're ready to actually do some of these. By the way, if your head is swimming a little bit, you're perfectly normal. There is a lot going on for this section, and that's why we're going to kind of spread it out. So we're going to do a couple problems here, and then I'll come back and do a couple more problems on the next video, and give us all time to get really comfortable with this thing. But let's start with this very first problem and just see if we can walk our way through all the things that needs to happen. So we'll look at section 9.3. So look at section 9.3, and it says, or exercise 9.3. It says, you know that when the speed limit is 65 miles per hour, the speed of drivers in Texas is normally distributed with mu equal to 67. Is that right? People in Texas drive fast, don't they? But okay. Is normally distributed with mu equal to 67 and sigma equal to 4. You're curious if the drivers on the loop are significantly different from those throughout the rest of the state. So you do a study on the average speed of cars driving on the loop on a Friday evening, and you measure the speed of 50 cars and find that X bar is 65.75. So let's write down our hypotheses. Let's see if this is a one-tailed or two-tailed test. Let's kind of talk about how we're going to study this and use our test statistic and then find our p-value. So let's go through all 4 of those steps and see if we can calculate something useful here. This would be a great time for you to pause your camera or pause your video. If you feel like the conversation that we did a minute ago makes sense, if you feel like you can make progress, it's a great idea to pause and just see how many of these you can get through. If all you can get through is writing down the hypothesis, that's perfectly fine. But maybe you could even make it to the end. So challenge yourself, pause your camera, and see how it goes. Okay, now that we're on pause, let's write our hypotheses down. So our null hypothesis. What is our null hypothesis? Our null hypothesis is the hypothesis that nothing happened. So if our drivers on the loop are the same as all of Texas, so the null hypothesis is the same as all Texas. So our null hypothesis would be that mu is equal to 67, because if our drivers are the same, then their speed is 67 miles per hour. But what is our alternative hypothesis? And that's where, by the way, we know it's going to be 67. The number is always the same for the null and the alternative. The only question is, what symbol do we put here? Are we testing whether it's greater? Are we testing whether it's smaller? Are we testing whether it's not equal to? Well, we read our question really carefully, and it says, you're curious if the drivers in the loop are different from. So notice our words here are different. different, and different, it didn't say different as in they're faster. It didn't say they're different and they're smaller. They just said they're different. So that means our alternative hypothesis for this problem is going to be a not equal to sign. Okay. So hopefully we're able to get those for our alternative hypotheses. And notice that we can already tell what our picture is going to look like when we draw it. So when we draw our picture, we're going to have a z-value, and I'm not sure which, our z-value will either be large z-value or smaller than, but once we take our z-value, we're going to end up shading both sides because we're not equal to problem. So that means we're going to have a two-tailed test. Now the next thing we have to figure out is we have to figure out which formula are we going to use. Well, we had two formulas. Our first formula was z equals x bar minus mu divided by sigma over the square root of n. And the other problem was, the other formula was t equals x bar minus mu divided by s over the square root of n. So how do we tell which formula we're going to use? So this is, this is part B right here. So how do we tell which formula we're going to use? Well, we have to read the problem carefully and say, does the problem tell us the standard deviation for the whole population, or does it just tell us the standard deviation for our 50 cars? If you read the first line, it says, we know the speed of drivers in Texas is normally distributed with mu equal to 67 and sigma equal to 4. So that sigma equal to 4 in that problem tells us that we are in this setup. So that means we are dealing with a normal distribution for this problem. So a normal distribution is where we're at. So now we're ready to go ahead. Once we know that this is a normal distribution, we're ready to go ahead and start doing some calculating. So let's find our test statistic. We take our z and we just try to plug all of our stuff into it. And so z equals x bar, which is from our sample. And so our sample is 65.75 minus the speed for all of Texas. And we know the speed for all of Texas is 67. And then we divide that by sigma, which is 4, divided by the square root of n. And the square root of n is 50, because that's how many drivers we have. So you put your numbers in, they go in just like this, and hopefully when you're done, that's what you get for the result. Now we're going to plug this in our calculator and get our result. And I'm gonna have to run out of the room and grab my calculator. Sorry about that. I told you these weren't going to be the most professional thing we've ever done. But okay, let's type this in your calculator. As we type this in, I'm going to show you something that students will often do that get it wrong. So first, we'll do the 65.75 minus 67. And then we'll do divided by 4 divided by the square root of 50. This is actually not going to be the right answer. So if you look at this, this is often something that students will type in and get the wrong answer. And what makes this wrong is that the computer always does the order of operations. So what this does is it divides this number by 4 and then takes the answer and divides that answer by 50. But if you look, we don't want to divide all of this by 50. We only want to divide the 4 by 50. So what I'm going to do, let's just regroup this up here. So instead, I'm going to put the whole bottom part in parentheses, and now notice the 4 gets divided by 50 first, and then the whole answer gets divided by 4. So make sure you're using the order of operations correctly, and I get negative 2.2097. So I'll just say negative 2.21. That sounds like a pretty good answer there. Okay, so this is what we have for our test statistics. So now all I have to do is I have to put that on my z distribution, which looks like this. And I've got negative 2.21 is going to be on one side, and 2.21 will be on the other side. And I want to find out this probability. Notice one side, the two sides are the same, except one is positive and one is negative. That's because the center here is going to be 0. Quick key, whenever we do this, we always use mu equal to 0 and sigma equal to 1. We're always doing a standard normal distribution. Why don't we use the mu and the standard deviation from our problem? The reason is because we have converted it to a standard normal distribution. We've converted it to a z by using this formula. So this formula makes it standard. It makes it where 0 and 1 are the right numbers to use. So what do? I just now try to find a probability. So let's just go in and find that using our calculator. Remember, we go to the distribution button and we go to normal CDF, and then most of you will have a menu, but I'm just going to type mine in. So we'll go normal CDF. And then for my normal CDF, my lower, I'll do like -999, like some negative infinity number. And then for my upper, I'll do -2.21. Mu equals 0, sigma equals 1. And so I'll type all that in. And hit enter. And I got for my answer 0.0135, but I need to multiply that by 2 times 2 to get my actual p-value, and my actual p-value is the result that comes from multiplying this by 2. So here, let me erase this, and I'll do point p equals, I'm going to take that and multiply it by 2, and that's going to give me 0.027. And so this is my p-value. So whenever you hear people talking about a p-value in your problem, what they've done is they've done this whole process to get to the p-value. And often when you read papers or or something like that, they often won't include all the details in the problem, but they'll usually include the p-value. And it's understood that this was the process they went through to get to the p-value. But notice that we started with a hypothesis. We then had to determine what type of tail we want. We had to calculate our test statistic. We had to use our normal CDF to calculate here, and then we had to find our p-value. Okay, there's one last question that we really want to ask once we get to this problem. And the last question to ask is, what should I conclude? What should I conclude? Well, to make a conclusion, I have to make a judgment. And my judgment call is this number an unlikely number, or is it not an unlikely number? And so there are only two possible conclusions that I could come up with. Conclusion number one is that P is very small. So if I think P is really, really small, and that is, I think that P is so small that this couldn't have happened by coincidence, then what I say is my sample could not happen by chance. And so notice that the odds of my sample or something on either of these outside edges happening just by chance is 0.027. So that's 0.27%. So that means if I were to just randomly gather 50 drivers and the real average was 67 and with sigma of 4, if I were to just randomly gather 50 drivers anywhere, that I would have a 2.7% chance of getting the number 65.75 or smaller, getting something this extreme just by chance. And so if your P is very small, we say this sample could not have happened by chance. And so what's our conclusion? We conclude that then we conclude that H naught is false. And what we write when we write down our answer is we write down this. We write reject H naught, And then we might put this in practical forms. We say the cars are not driving 67 miles per hour. Okay, so that was one possible outcome. But let's look at option B for my conclusion. So for my conclusion, I've got option B. Option B is that P is not very small. P is not very small. And if P is not very small, then that means we could have gotten happened by chance. So if P is not a really small number, so suppose P was like 50%, then you might go, oh, okay, these drivers, there's a 50% chance that my drivers would have been going that speed anyway if they were all traveling 67. And so if that's the case, then our conclusion is that H naught is not false. Now, this is an important distinction. We never conclude that H naught is true, because is the mean actually 67, or is it 66.95 or 66.885? I mean, we don't know that the mean is exactly 67. You can never conclude that it's true. But all you can do is you can conclude that you have not proved H naught false. And so what we will say is we will say we fail to reject H naught. And that means that there is not enough evidence to show that cars are not driving 67. So we haven't said the cars are driving 67. We've only said there's not enough evidence to conclude anything else. This is why it's important that your H naught, whatever your, this is important that your H naught, your default assumption, is what it should be if there's nothing interesting happening. So notice our H naught was always the nothing to see here assumption. So for our problem, H naught was that our drivers were the same as all of Texas. So if we don't have any evidence to point in the other direction, the most logical conclusion is to say, they're all the same as Texas. And so H naught is your assumption that should be true if nothing's happening. And so therefore, if nothing's happening, the most logical conclusion is say, okay, 67 seems about right. But if you can conclude, if you get a P that's very small, then you say 67, this couldn't have happened by chance. And so therefore, my 67 had to have been false. Okay, this brings us to an important question. An important question is, how small is small enough? So an important question is, how small is very small? Okay, so that's a good question. How small is very small? Well, the answer is it's a judgment call, and it depends on every person and every situation. But this is what we call alpha. Alpha is the level of significance. Uh-oh, I got some letters wrong. Alpha is the level of significance. And what alpha is a choice for what point is your cutoff point going to be. So in some research studies, you might say alpha, if it's less than 10%, if there's less than 10% chance of it occurring, I'm going to say that's small enough to go out on a limb and say that the null hypothesis was probably false. Some people will say, no, I'm not comfortable with having a 10% chance that it could have happened that it could have happened anyway. So I'm going to require it to be a 1% chance. And so I'm going to say that alpha must be smaller than 1%. And so anything that's less than 1% likely, I'm going to say couldn't have happened and that H naught occurs. notice your tolerance for how small alpha is going to be is going to depend on your problem, right? If you're, once again, if you are a business just measuring whether your ad revenue has increased or whether your ad revenue has increased your sales, maybe 10% is enough. So if you have if you get a p-value smaller than 10%, you're like, hey, this is good enough. I'm willing to go ahead and make a bet and keep going in this direction with our ad campaign. However, if you're NASA and you're trying to prove that there's life on Mars, you don't want to come out and make a press conference and tell the whole world that you've concluded there must be life on Mars when there's a 10% chance that your results could have happened by chance, right? You would want to be much, much, much more confident than that. So your level of confidence depends on your problem and where you set. So alpha is chosen, and ideally, alpha is chosen before the problem starts. Now, so in an ideal situation, the researcher, before they ever start their problem, they say, I'm going to reject alphas that are below. I'm going to make alpha 0.05, and anything less than 0.05, I'm going to reject. Anything bigger than 0.05, I'm going to fail to reject. In practice, researchers don't always do this, but you can see why we might want to do this. The reason is, well, getting a really small p-value, being able to say, I reject H naught, is a really good result. So you might be tempted to kind of fudge that alpha value if you get kind of close. So don't tempt yourself to fudge the alpha value. Choose it before you start. For our class, this will come from me. Or the textbook. So if you're doing a textbook problem, the textbook will say alpha is 0.05. If I give you a problem on a quiz, I will say use alpha equal to 0.1 or something. So that number will be told to you when you do problems. But when you get out in the wild, you'll have to make your own decision on what alpha. One standard in science journals, alpha equal to 0.05 is a standard. So in that sense, that if you're writing for some sort of science journal and you're not doing something like trying to prove that life is on Mars, you're just doing a standard run-of-the-mill science experiment, 0.05 is a pretty common standard. So based on that result, which conclusion would I do if I used alpha equal to 0.05? If 0.05 was my alpha that I chose, I would compare my p-value to 0.05, and what I would say is I would say that my alpha value, I would say that 0.027 is less than 0.05, so that means p is very small, and so that means option A is what I would have. So if I were doing this problem and alpha was 0.05, then my conclusion would be that we reject H naught, the cars are not driving 67 miles per hour. However, if someone else comes along and they decided they wanted to use alpha of 0.01, then all of a sudden they would have a different result and they would be in option B. So what you choose for your alpha actually matters. Okay. I was going to do some more, but I feel like this is a pretty good start. So I'm going to go ahead and stop the camera here and give you a little bit of time to catch your breath and think about things, and then we'll come back and we'll do the rest of the problems.